So I should start. Yeah. All right, welcome everybody to today's session. So it's a pleasure to introduce Jacques Blevici from Sorbonne University, and he will talk about stationary Vlasov fields on Schwarzschild.
Well, thank you very much, Mihalis. Thanks to all the organizers. I'm very happy to be here. I have to say that hearing some of the previous talks, already yesterday, sort of reminded me of the last time I was here. It comforted me a little bit about the talk I gave, because the topic was holography in ADS, and I talk about the stability of Minkowski space with Vlasov matter. Anyway. So the talk will be about some joint work, which is work in progress, with Renato, but also Boris from Imperial College. And well, I am, I can redeem myself because this time I will be able to stick to the topic a bit better, because there will be a black hole since I will talk about Schwarzschild. Okay, it will be a fixed Schwarzschild because I will talk about just the linear Vlasov equation on Schwarzschild. Okay, and the energy tensors of such fields, etc. So to remind you quickly, okay, so Schwarzschild, let's call it. So I will only look at the exterior. Okay, you can just think of the standard θ coordinates for the exterior. That will be enough for what I want to talk about. Let's call the exterior, let's say, I don't know, mx, and then G sub m for the metric of Schwarzschild. M is the mass. Okay, so let me briefly remind you of what the Vlasov field is. So F will be the main unknown. It's like it's a distribution function. So distribution function. So it's a map from so-called mass shell to, let's say, R plus. The sign will play no role in what I will say. And then P, what is P, this mass shell? It's a set of all points in the tangent bundle, such that X will be here just in the exterior, because I will only look at the exterior. And then P is a future directed and normalized to -1. Okay. And then, I mean, I will, of course, look at the energy momentum tensor generated by such F. So this will be P mu nu of F, okay? It's given by an integral where you just sum up all contribution at a fixed x, at all p's, okay? So it's an integral of F. You look at the fiber in P at each point x, and then you integrate this with two moments, so P mu, PV. And then there is a volume form. But okay, for practical purpose here, at every point x, okay, because of these relations, you can parameterize any such p just by these, like the spatial part of p. So you can write this as an integral of, let's say, R3 in p of f. This would be at the point x, okay, of xp, p mu, p mean. Then there will be a volume form, p, let's say, p1, p2, p3 over, so p naught is positive, but p naught downstairs is negative. So that would be the volume form. Okay. So finally, our F will be required to verify the PDE. So the Vlasov equation will be such that F is constant along time-like geodesics. Okay, and if you write this in, let's say, local coordinates, that looks like this. T P gamma F. Okay. Now I have a little bit of material about the geodesic flow and other things on Schwarzschild to introduce. So I thought that in order to keep you motivated, I should start with the punchline and then I'll introduce the material. Okay. So the punchline is the following. I will try to convince you that there exists smooth, compactly supported initial data, let's say F naught, let's say at t equals 0, at t equals 0, for, let's call this V, let's say Vlasov, for V, such that if you consider F the solution arising from F naught, then you can look at its energy momentum tensor. Okay, so that's a priori dynamical quantity. And the claim will be that, at least in a pointwise sense, with even quantitative rate, this this is there exists, so it's not necessarily for all. Okay, I'm not saying that. But you can construct such a priori completely regular initial data so that the limit of the energy momentum tensor in time converge to an energy momentum tensor of a stationary solution to the Vlasov equation. So here stationary Vlasov will mean that okay, it solves V and dt of F is equal of F stationary is equal to 0. Okay. Well, this is maybe not so surprising that this can happen, but what maybe less intuitive is that this T station of this stationary state will be not smooth. Okay, so there is in the evolution a lack of smoothness that can occur, and I found that an interesting fact. And of course, for this to be occur, because T is a functional that take a Vlasov fields and give me a function. This is a smooth operator a priori. So the only way this can occur is that F stat also will be not smooth. And it will also, it is a solution, huh? So it's not like a lack of compactness or anything like that. Okay, so this is a punchline, and now I'm going to try to convince you that these objects exist and that these things can happen. So for that, I have to talk a bit about the time-like geodetic flow on Schwarzschild. Okay. Okay, so the first thing I want to say that we can split the geodesic into two families. Okay, they are what you can call, okay, for lack of better name, dispersive geodesics. Okay, so imagine that I don't know. This is like the event horizon. This is like the past. Okay. Then the dispersive, this is like the R equal. I don't want to draw Penrose diagrams because it doesn't capture R equal infinity in the way I want to for this time like geodetic. So these dispersive geodesics, okay, there are different versions. There are some that, so they are either connected to, H minus. So for instance, they can do something like this, okay? Or they can go from H minus to R equal infinity, or they can, emanate for M equal infinity and end up into the black holes. Okay, there are versions like this. Okay. And then the other set are bound geodesics or bound orbits. Okay. So what these ones do is that they oscillate between, I don't know, some smaller radius and a larger radius R1 and R2. Okay, so this is a geodesic, let's say gamma of t. Okay, and if you look at the radius of gamma of t, it sort of stay between some R1 that doesn't see the black hole and some R2 that doesn't see infinity. Okay, and contrary, let's say, to the null geodesic flow that many of you are maybe more familiar because it's linked to stability of black holes and waves. When you look at the this bound or this trap orbits, there's a very large family of them. It's sort of filled an open set in phase space. Okay. Okay. Yeah. Strictly less, not equal. And the other one also, they don't.
You're saying these are not the endpoints.
Not necessarily. Yes, if you wanted them to be the endpoint, then you can do that. Okay. 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 So the way you can, of course, do this is by looking at, you can remember that the flow is integrable. Okay. So if you introduce, I don't know, Ct, which will be like the killing thing. So this is d by dt. Ci, which will be like the killing fields, the three killing fields of generate the SO3 symmetry of Schwarzschild, then you know that for any geodesic that quantities like this, Ct, and also this, these are constants of motions along the flow. And let's call this the energy. So for signs, we put the -1. Okay. And okay, I will not look at the most general case. I will look in the case where the Vlasov fields are have also a spherical symmetry in the sense of Vlasov fields. It's not the lifted symmetry. And so I don't need to know here everything, especially to classify the geodesics. I don't need to know everything about the angular momentums. I only need to know, let's say, the square of this sum over E from 3. So this I will call L squared. Okay, so this is angular momentum square, the total angular momentum square. We will say symmetric, not the Vlasov field set. But what it means is that the Vlasov field F that I will consider, I can parameterize them as function of T, R, PR, and the total angular momentum. That would be enough to parameterize them. Okay. Okay. And now, so I want to keep that. So I will write it here so that I can keep this picture. So let me not, give you a full classification of all the time-like geodesic flow. Is relatively complicated. I mean, it's not completely trivial. Okay, so among other things that are conserved, of course, you have that the lengths of the vectors are concerned. Okay, and this is the same as saying that the energy is equal to PR squared plus some effective potential that depends on R. And the effective potential is just 1 minus 2m over R times 1 plus L squared over R squared. Okay. Okay, so let me introduce the set of parameters EL, okay, such that these are necessary conditions to get a bound orbit, okay? So I will call this the set A bound. So this is a set of E and L squared, okay? And the conditions that are E belongs to square root of 8 over 9, 1. I should say as well that there are some endpoints, which I will talk a little bit about it, where you are still, I'm excluding here, for example, the endpoint square root of 8 over 9. I will talk about this extensively later. These are also bound because they correspond to such stationary points of the flow, okay? You need L to be bigger than 12m squared. And then there is a condition that L must be sandwiched between two curves, one which will be the upper bound curve, and the other one which is the lower bound curves. Okay, I will tell you in a minute how you construct these curves. Okay, they are explicit, but they are a bit ugly, so I will not write them down. But I can draw a picture in the in the E, so this will be L squared, and this will be E. Okay, so I have square root of 8/9. Then I have 1. Okay, and then this curve LLB looks like this. Not 0 here. Here I have 12m squared. Okay, and the other curve look like this. So it has a different slope. Okay, and then it goes to infinity at 1. Okay, and this is the A bound is somewhere here. Okay, so sorry. Sorry, thank you. Better? Okay. So already I can tell you how it's going to be. Okay. The lack of regularity that you will see in the energy momentum tensor is connected to the fact that this picture is not like completely regular. Okay. Essentially, there are different boundaries in this to this region, and you will have different properties near the different boundaries. The lower bound here, no, sorry, the upper bound, okay, is actually good in the sense that if you look at what's going on near any of the point of the upper bound, you will find that things are relatively going well. For instance, the period of the orbits is goes to some extends continuously to any of these upper bound curves. The lower bound is bad, and the period, for instance, goes logarithmically. It's going to blow up. Okay, this point is really the worst point. Okay, in physics, this is called the innermost stable circular orbits. So it's sometimes called ISCO. And then what's going on at 1, especially near this point, so this is actually 16m squared. This is also bad. Okay. And from what I could find in the literature, especially in the physics literature, but also in some, math things, this when you approach the good part, where things sort of the period is extends, sort of things smoothly, etc., this can be covered by previous things you can find. But the analysis near here, also near here, and near here, I think is had not been observed before. This is what we found. Okay, now let me just briefly tell you what are these curves. So this corresponds to, let me draw another picture. There'll be lots of pictures. Okay, so peak E and L squared in A bound. Okay, and then I will draw the effective potential in terms of R. Okay, and it looks like this. So you can see that the 2m, it has to go to 0, then it has a bump, and then it goes back to 1. Sorry, this one is really not the one I should draw. Okay, something like that. Okay, and there is another possibilities which can occur, which is that it goes like this, but the 1 is kind of above. Okay. The two different pictures are not so, the fact that there are two pictures is not so important, but for correctness. Okay. So in particular, so now if E is this range, what this means is that if you draw your E equal constant, so your energy curve, you should see 3 roots like this. Okay. So these three roots, I will label them as R0. So it's a function of E and L. And this is like R1. And this is like R2. Okay. And now the case where you reach LLB of E is when actually, for instance, in this picture, this would be, the E, and this will be a spatial potential that depends on E, which is VL of LLB of E. Okay. And if instead you were going to reach, which means that, okay, this lower, the LB stands for lower bound because it's the lower bound of L. Okay, but this is where you reached the top of the potential, not the bottom of the potential, because the behavior is very different. Okay. And if instead, like you, if this was LUB of E, then this means that you would be looking at a case where the energy is at the level of the bottom of your potential. Okay? Okay. So in particular, here you see, so this is E. Here you see three roots. This is kind of the regular case. Okay? And here you see two roots only, okay, which are either these two ones, okay, or it could also be, no, not this one, these two ones, or you could have, in that case, you have this one and this one. Okay, that roots. Okay, finally, the cases which are very bad is the case where E is equal to square root, this is the ISCO point, so this one and L equal 12m squared, I think. And in that case, you get one root, or if you get a triple root. So somehow I've also now been involved in, not even ODEs, just polynomials, but okay. There is also another funny case, which I will talk a bit less, but somehow the analysis is also interesting there, which is E equal 1 and L equals 16m squared, L squared. And this is actually one root, but for a different reason, because then the potential look then in that case, the polynomial, so the polynomial is really take this, okay, so it's really E squared minus VL of R. You can call this PR of E and L. Okay, and if you would please formally multiply this by, well, not formally, if you multiply this by R cube, then you get a polynomial of order 3. And this case is when the polynomial becomes not of order 3, but it degenerates to a polynomial of order 2. Okay. And then it looks like this. You get, this is 1. You never reach 1, I mean, it's asymptotically. And then you touch this point here. Okay. Now, if you look at okay, maybe it's a good time to talk about stationary Vlasov field. Okay. From that picture, you could ask, how could you construct a stationary Vlasov field? Okay. So it's not so complicated. You can do the following. You can choose B, which is compact, which is included compactly in A bound. So I don't forget how you write this, but something like that. Okay. So it doesn't touch the boundary of A bound in particular. So it's something that lies, I don't know, here. Okay. Now you would choose a profile phi. Just take any smooth function, which is we support in B. Okay, and then you would let f of R PR L squared to be equal to phi of E. Here E will be okay, you'll have to compute what E is in terms of the R in PR and L, okay, and L squared. And because these are constant along the flow, then this gives you a stationary things, okay? So this is somehow related to some sort of folklore theorem in kinetic theory, which is Jean's theorem. I'm saying folklore because it's somehow believed to be true in many scenarios, but in some scenarios it's not really true as it's typically presented. So this is related to Jean's theorems, which is that in general, stationary solutions should be just functions of the invariant of the flow. Okay. However, if you look again here to this picture, you see that if you fix E and L squared, there are actually two orbits which are possible. There is an orbit which will go like this, and then there is the periodic orbit that goes like that. Okay. And if you only take a functional like this one, then it will have support on both orbits. However, these orbits are not good, and if you assume that you have this profile and you also keep this type of orbits, then if you compute the energy moment tensor or the particle number, total particle number, then it will be infinite. So it's not very good. So you have to exclude these ones. Okay, it will correspond to an infinite flux. Okay, which is logical because you imagine that these ones they go into the black hole. So something is feeding the black hole for all times. This is not possible. So to exclude them, then you just multiply by a cutoff that select this orbit. So for instance, since this is R0, if R is bigger than R0, then you don't see the one on the left. Okay. This cutoff, I claim you could even take it just to be a characteristic function of that set. And the reason why you could do that is because the transition from, let's say, 0 to 1 would occur in a region where the profile phi will be not be supported. You could arrange that to be true. Sorry. Okay, this is linked to the fact that since you choose B to be compact away from A bound, you never approach the top here. So you never approach really the transitions from this type of orbits to this type of orbits. And by compactness, you will have a gap. Okay. But the fact that you need to add these things, okay, this means that Jean theorems is not true in relativity. It is true, for instance, for Vlasov-Poisson in spherical symmetry. There's an old paper of Bat, Faltenbacher, and Horst that prove that. It's essentially just about proving that the gravitational potential is single weld. Roughly the proof. And this fact was first, let's say, highlighted and proven for the ancient Vlasov system. By Schaefer in a paper from 98. Okay. And like a different proof of this, also for the ancient Vlasov system, was given by Fatima. It's after a posteriori fact from one of the work she did in her thesis, so in 2021. Okay. Now it's a good time, since I already started, to talk about some literature on the subject and things which are related. Literature. Okay, so I won't be exhaustive, but I won't talk about the things which are most relevant here. So the most relevant one is a work by Renato Velozzo from his thesis. Okay, so this is 2024. So what he did is that he looked at F, okay, solution to the Vlasov equation, the linear Vlasov equation, again on Schwarzschild, linear on Schwarzschild, okay, not necessarily spherically symmetric in this work, which was C0 with compact support. And then he introduced a characteristic function of what? Of the dispersive orbits. So this just project F only on the orbits which are not trapped. Okay. So when you look now at f times this object, you can look at its energy momentum tensor, and Renato will tell you that this converges to 0 as t goes to infinity with some rates, okay, which depend how you approach infinity, in terms of u, v, r, etc. Okay. Okay. So d here is dispersive. Okay. Then there is another set of results which are tied to mixing. Okay, so this is a general belief in it's not a belief, but it can be proven in many situations in kinetic theory. So the mixing phenomena in general is that if you consider, let's say, F, we support only in let's say the trap or the bounded orbits, trap region, let's say, then we expect the energy momentum of F to relax to the energy momentum tensor of a stationary solution. Okay. So this goes back to work of Linden-Bell. This is supposedly true for Vlasov-Poisson and maybe ancient Vlasov and things like that from '62, and also work of Landau, which considers similar issues in the plasma physics case, but the equations are not the same exactly. But okay.
When you say Einstein-Vlasov and stationary, you mean there's a common healing field for both?
Yes, it's the same d by dt.
Vlasov you consider them Schwarzschild. That's not the case, right? Schwarzschild has its standard healing field with rotational symmetry. And the Vlasov matrix construct has another.
No, it's the same. D by dt. It's a lift of d by dt to the tangent bundle because it's not. I'm French. In the Bourbaki sense, it's not the same. But oula. Okay. Okay, so then there are many works, so maybe I can add them here, about mixing, okay, which not necessarily, okay, I will just quote a few works, but I don't want to spend all my time on that. So I can quote, for instance, mixing without a rate, okay, which means that you have a type of relaxation of this form, but you don't know at which speed, and there is no, actual quantitative estimate. So this was done first by Rioseco and Sarbar. So they have several works. They have works that concern Schwarzschild. They have works that contain Kerr, in different situations. And this is also, really in the case where the support stays away from the boundary of this A-bound region. Okay. Okay. Then there are many other works by people connected to either Rioseco or Sarbar in this range. Okay. So there are also, for instance, mixing with a rate, but not for Schwarzschild, for some model problem involving trapping potentials and things like that. I will not go through all of this. There are also works about quantitative mixing. So this is quantitative by Chaturvedi and Jonathan Luke. So there is one from 2022 where they consider like a 1D model problem with a trapping potential, again staying away from the analog of the A-bound region. And then another one from 2024, which is more of a 3D model. So again, you have some sort of trapping potential. In this case, they look at linear quantitative mixings, but also the implication for nonlinear problems. So they also cook up a nonlinear problem for which they can show a long time existence compared to the the local existence that you could get. Okay, and then there are also several groups which also study both quantitative mixings and also like linearized ability including on a non-trivial stationary states. So when you look at the linearized equation on Schwarzschild, you get just the linear Vlasov equations, but you could linearize on a stationary solution, which is not Schwarzschild, which is close by to Schwarzschild. This gives you something more complicated. So these type of things were studied in particular. Let me not write all the names, but I will say them because they worked quite hard on this. Gunther, Rein, Straub. There is work by Ajik, Rein, and Schrecker. And there's a more recent one of Ajik and Schrecker from 2025, where in particular they study mixing when you approach the top boundary, okay, which corresponds to this elliptic point in the picture, okay, and where their analysis extends to this part. Okay. Finally, there are also many studies about the constructions of stationary solutions. Maybe I can put this here. Stationary solutions, okay. So in Vlasov Poisson, there are many things. I will not go through this literature. In the case of ancient Vlasov, there are also many things. I will only quote here the ones which are directly relevant to what's talking here, which is the initial work of Rein from 94, the work of Schaefer, which I already mentioned here, from 98, and then the work of Fatima Jabiri. So she has one where she sort of looked at stationary solutions nearby Schwarzschild, starting from Schwarzschild. This one is from 2021. So this is Schwarzschild. And then she has another one where she studied this, but by perturbing Kerr. So this is stationary solutions which sort of deform Kerr. Okay. Having introduced all of this, now I can tell you. Yeah.
So the ones that you start with Schwarzschild, you obtain stationary coupled solutions.
This is the ancient Vlasov, yes. Ancient Vlasov. Spherically symmetric, and this one is axisymmetric. Yeah. Yes. Okay. So what I want to do now is to imagine the following things. The reason why somehow I want to consider all these boundary points is because I see no reason why you should not. So if you imagine that you just take some profile in ENL, okay, and you just assume that your profile has a support near this point here, for instance, okay, you can cut this profile so that far away is sort of 0, but here it's just exactly a function of E and L squared. This gives you a perfectly smooth function of R, PR, and L squared. And there is no physical reason that I can think of to exclude those. Okay. So if you do this, where can I go? Maybe here. There's too many boards. I'm kind of lost. Actually, I should check this picture. This one is less useful. Okay, so take such an F, which is this property here. So we support, okay, containing, let's say, which is square root of 8/9 and 12 and squared. Okay, containing an open set around this. Huh? Open set around point, okay, and also assuming that when restricted to the A bound, so F restricted, let's say, to the bound orbits, as exactly this stationary looks like this, but then you need also this cutoff key R bigger than M. Okay. Then if you look at F minus F restricted to the bound orbits, this is exactly the F restricted to the dispersive region that Renato studied Okay. So we know because of this that the T of the F must converge to the T of this F, let me call it F status stationary. And the question now is, can we sort of describe this object on the right? Okay, and so the theorem looks like that. So with F stats as on the left, let's say, you have that when you look at TF stats, so you can show that it is 0 for R less than 4M. It is C infinity on 4M, 6M, which is already non-trivial because, okay, of course, you will have to look at why it's sort of, there is an obstruction there, but because of this includes this lower boundary here where things are a priori, when you look at the corresponding integrals, they look singular a little bit there, okay? Okay, so in fact, it is C infinity on that set. And if you compute the derivatives at any order, they have limits of 6M and 4M. Okay, so it's really C infinity on the closure, if you want. Okay, it's also C infinity on 6M plus infinity, including 6M in the sense that if you take limits, I don't know, somewhere on the right of 6M, and then you take derivatives, sorry, on the right on 6M, and you mush that to the 6M, then you will find limits at any order. But there exist, let's say, F stats. Okay, it's actually it's a generic thing that also follow from the proof, but here I will state it only in this way, such that the limit as R goes to 6M, let's say minus, so this is R less than 6M, at derivatives. So it's also, first, it's also C0 everywhere. Okay, it's C0 on 2M plus infinity. Okay, so it's continuous. But if you look at, let's say, the first derivative of this, T F stat, on the right, it doesn't match, so d by dr, this is a function only of r, it doesn't match the limit on the left. Okay, so they don't agree. So it's not smooth in this sense. Okay, and the same is true as well near 4M. But with 4M, okay, you have to go, depending on the, 4M is a bit funny, which is that the regularity at 4M is tied to the decay of the field near infinity. So that's not obvious, but if you were to give me a profile which is compactly supported in the sense not in A band but in R, then it will actually be smooth at 4M. But if you have some tail, then it will not be smooth at 4M. Okay, so now I have maybe a couple of minutes to try to tell you about the proof of this. Okay. So there are a couple of key ingredients, but okay, you need some study of you could say fine, but I don't know. That's sort of fine properties or properties of the roots. Okay, of E squared minus VL of R. There is a relatively lengthy reduction of let's say this. So you view this as some form of integrals and you work again and again to try to transform this to some sort of tractable integrals. Okay, which they will not necessarily be okay. Yeah, the integrand will not necessarily be always perfect, but you can find out whether they are singular or not. Okay, and here there's quite a lot also of monotonicity properties associated with either the roots or the polynomial that we monotonicity, which some of them I will mention to you. Okay, so let me try to do part of this reduction, and when I need the properties of the roots, I will essentially quote them, and you can believe me or not. Okay. So let's look at something like this. Okay. So it's an integral in P of the F stationary, okay, with some P weight and some measure depending on P. Okay, it will not be precise. And what you do with that, you rewrite them in terms of an integral in the energy and an integral with respect to the angular momentum L. Okay. So remember that everywhere F, where can I write that? F will be always equal to this cutoff times this profile. So here I have the cutoff, and then I have my profile. Okay, and then I have a volume form, and because of the change of a variable here, I have a mildly singular denominator, which is this one. Okay, so this cancels the roots at the turning points. Okay, so but okay, if you only had like these things with no boundaries to be approached, this sort of follows the analysis of this type of integrals by sort of classical type arguments in ODEs, Hamiltonian PDEs, like similar to computing periods in action angle variables. You'll find them relatively easy. Okay, so of course there is a condition for that square root to make sense, which is that E squared must be bigger than the potential. This, you can convert this into an upper bound for the maximum L allowed at fixed E. Okay, so you can rewrite this as an integral. Here in this cutoff, you remember that also, I forgot to say that, sorry, which is that, remember that I was taking some bump here near the ISCO point, and then I was projecting on a set of bound orbits. Okay, this means that I also multiply by the characteristic function of that set A bound. So here I have this cutoff, but I also have like a characteristic function of the set A bound. And this is a function only of E and L. Okay. So in particular, being in A bound means that E is restricted to square root of 8/9 and 1. So here I have this. Okay. Then I have an integral from 0 to L max. Then I have the two cutoffs, and then I have the profile dE dL. Sorry, and then I have the denominator. Okay. Okay. Now I'm asking myself. So in this cutoff here, there is also the fact that L must be above this curve, and this curve is LLB of E. Okay. So the question becomes whether this lower bound here is above this L max. If this is the case, then it doesn't contribute because it's n0, or whether it's below, and then I have this gives me a lower bound here. Okay, so the question becomes whether when do we have L max of E and R bigger than LLB of me? And the answer is if R is bigger than 6m, then let's call this, let's say, star. Then star holds if E is equivalent to E is bigger than some minimal energy. And if R is less than 6m, then star is always true. Okay, so let me describe what is this lower energy bound. There is a lot of, there is many of these things throughout the proof. So you already see that there is some sort of asymmetry between 6m and the other part, but there will be more such things to come. So, okay, this is where I wanted to keep this picture here. Okay, so forget about the blue curve, matter. Okay, so this is an energy, okay, and this is a spatial potential. This is not any potential. This is potential where I choose the angular momentum to correspond to the lower boundary of this E. So this curve here, okay, which means that the energy sort of grazes the top of this potential. So here I have a double root, and here I have a single root, and this single root is R2 of E, okay, and E2 of R is the inverse of R2 of E. So this is the inverse. So it turned out that R2 of E is strictly increasing, which is not totally obvious. It's not R2 of E is not given by any tractable functions you could think of. And this is the inverse of R2 of E, which I claim is monotone. And it's actually monotone only for R bigger than 6m. So, okay, so why is this true? This I can explain relatively easily. Okay, I have it somewhere here. Okay, so imagine that you are looking at R on the right-hand side of 6m. So 6m will be somewhere here. Okay, and then what is this curve? The condition, this condition here, L max of ER is bigger than LB of E. This is the same as E squared is above the potential, but the spatial potential corresponding to this lower curve. Okay. So you look now at the picture and you say, this is the potential and this is E. Why do I need for this E to be above the potential? Well, I need R to be less than R2. Okay, and less than R2, using the inverse, this transfers into E bigger than E2. Okay. Okay. So I'm going a bit late, so let me try to rush off. So, okay, you do this a couple of times, this kind of a reduction. And then in the end, you sort of do also many, well, not many, but two of the change of variables in the integrals. And you reach a state where the integral looks like that. You have an integral. Let's say I'm looking only at R bigger than 6m, because you have to treat these two regions separately. Then the integral will look like this. This would be 1. Okay, then there will be a prefactor. This comes from some Jacobian in the change of variables. And finally, that prefactor has a power of 1/2, which is a bit worrisome because of typical square root lack of issues. And then there is the remainder of the integral in L, which now, after I've stretched using variable and things like that, will look like this. I have my profile. Depends still on E, and then it doesn't depend on L because I've used change of variables. It depends on some function L tilde, which I will not specify, that is a function of S, R, and E. Okay, and then it has a ds over square root of 1 minus S. Okay. The point is that this function is smooth. At least it's clear when you're away from any boundaries. Okay, so you could take derivative in R as many times of this. It doesn't matter. And this weight that you see here, okay, it's regular at s equals 0. It's singular at s equals 1, but it's just integrable at s equals 1. So you can differentiate this as many as a time. However, there's still this problem here because this object sort of vanishes. So there is a square root. Okay, it's sort of a complicated expression in terms of E. and it vanishes at one at the bottom. So you still have to be worried about that. Okay. This I claim that you can actually use as a change of variable in E. So there is still an integral in E. You can use this to define this as, let's say, P of E and R. Okay. You can use this as a change of variable in E to get rid essentially of that obstructions. But for that, you need that things to again be sort of monotone in E, which it is. So the important fact is that dP over dE is positive. Okay, for as a as a function, it's a you fix R bigger than 6m, then you can prove another monodicity property of that object here. Okay, but this lower bound sort of degenerates as E goes closer to square root of 8/9, which is an issue near square root of 8. Okay, and now okay, I'm lacking time, but so using these extra things, you can show the regularity, let's say, for any point R bigger than 6m. You still have to work for R equals 6m. And in fact, it's not, this is where we spend most of our time. And the idea to treat R equals 6m was to use another change of coordinates in E. But this change of coordinates in E, so we change it to E of Y. This was tied so that you could see something in the expressions here to really split this sort of polynomial in R and E as something tractable. Okay, so the way we found it is by looking essentially at the expressions that you have for LLB. In this expression, there are some specific square roots, and you try to you cannot linearize these square roots, but you can try to make them like fractional relations which are regular. Because one thing also I didn't mention is that this function LLB of E, okay, it's actually not a smooth function at this point. It's C1 1/2 near square root of 8/9. Okay, meaning that if you take the second derivative of this, it doesn't have a limit here. Okay, so let me not write down the change of coordinates E of Y, but what I can tell you is that if instead of looking at PRE, you write in another coordinate, which is X and Y, and here X is just R minus 6m, and Y is sort of the inverse of that thing, then you see something tractable because this sort of split into this object here. Just something like this, and then there is a denominator, but which is regular. Okay, so the denominator doesn't matter. And here you see just the product of two polynomials in Y and X, okay, where you can compute the roots explicitly and you can do all the computations you want because it's very easy. So that change of coordinates is magical, but makes things work. And so you can essentially rewrite this, a lot of complicated integrals, is an integral with respect to X, with respect to, okay, there is another change to do for Y, but we forget about this one for a minute. And then you get some sort of expression which look like an integral with some sort of kernel in X and S times some, something that still depends on the profile. And that kernel you can show, which is integrable with respect to S. This is an integral in S. And moreover, that the derivative of this kernel stay bounded, are still integrable, okay, with slightly different bounds. So you can close. Okay, on 6m, less than 6m, there's a similar analysis, which is not quite the same, but close, okay? And then near R equals 4m, again, there is a similar game to play, but which is a little bit different because the reason why 4m is tied to infinity has to do with the fact that there is the limiting profile look like this. It goes to here. This is 4m. Okay, and this is equal 1. Okay, so because of the fact that somehow the limiting profile, which this is really the you cannot buy particles below 4m. Okay, this is connected to R equal infinity. Okay, I will not have time to talk about this, but thanks for your attention.
So, are there any questions?
So the fact that this matter distribution seems to have jumped something like a jump of
Yeah.
the level of the derivative? Is this something that physicists have discovered before, discussed? Does it come up in other non-relativistic contexts?
As far as I know, I looked, okay, and I couldn't find anything like that in the physics literature. What you can find is that because they don't, okay, the reason I think it's because you have to look at this Vlasov things. The nonlinear version of this is I don't know at all what's going on, I should say, okay. What is known is that if you take like individual geodesics and you look what's going on near this point, then the physicists have some, from the fact that the period sort of blows up here, this is known. The fact that the period blows up here, this is known. We actually analyzing the period, we found that the period blows up here in a non-uniform manner, depending on the angle in which you do this. So for the people who like blowing up corners, you have to do a blow up of these corners. At least that's how we do it. And this also, I don't think had been seen by the physicists, for instance. As far as I looked and asked.
So is there a conjecture for the rate that things would approach stationary state?
I don't have one.
Maybe Renato has the rates for if you don't have that, but yeah.
So if I don't stay close to the boundary,
he proved some rates. I'm wondering, but there are no conjectures for.
I have no conjecture about what's going on at this point. I think the next step I want to do is first whether to see whether this kind of even if you look at like the nonlinear Einstein-Vlasov but stationary, I do not know whether at the moment even the linear case, yeah, okay.
Maybe you avoid that point without the other. If you just mix something that's like
I see regular. This I think should be in the I think in the paper of Hajic and Schrecker, this should be there, but I don't remember the rates.
Okay, thanks.
It's finite. That I can remember that it's not like Landau damping where you can do it infinitely many times.
Is this the worst kind of sort of asymptotic singularity that you should expect? No.
No.
So what is the worst?
So the worst, okay, which is a work in progress, is that the problem is that here I'm looking at profile, large phi, okay, which where the profile, I forgot, I wrote it somewhere. But the function f, was this profile times some cutoff, okay? And all the singular part came from this cutoff. But you could ask the following, okay, here I justified that this was a good thing by saying that you can generate those by looking at the dynamical problem. But now what if you start with a solution which is not stationary in the trapped region, okay? What kind of stationary profile should you expect it generates? And the fact that the periods blows up at various parts lead me to believe that this stationary profile will not be smooth in ENL. And so my early computation suggests that the smoothness on the right side and the smoothness on the left side is destroyed in that picture, and that you get C4 1/2 regularity. Okay, okay, this is work in progress. I still have to check a few things. I think it's correct, but okay, we'll see.
Any final questions? Well, if not, let's thank Jacques once more. You ready?
Yes, ready when you're on.
Very good. So it's a pleasure to continue the session with Sam Collingbourne from the University of Edinburgh, and he will talk about uniform boundedness for linearized gravity on black holes from the canonical energy.
Thank you very much, Mihalis, for the introduction, and thank you for the invitation. I'm very sorry I'm not there in person. Hopefully soon I will be able to travel a bit more again. So as Mihalis said, I'm going to give a techniques talk and try and promote the use of canonical energy for linearized gravity. So I'm going to talk about obtaining estimates for linearized gravity on black holes from the canonical energy. So let me give you a brief outline of my talk. So I know there are many experts on the stability problem in the audience, but for clarity, I'll give a very brief review of the black hole stability problem. I'll then introduce the main technique protagonist for the talk, which is the canonical energy, and talk about conservation laws, or the problem of conservation laws for linearized gravity. I'll then introduce the spacetimes that are going to be the main spacetime protagonists for this talk, which are Schwarzschild in 4 and more dimensions and the Reisner-Nordström spacetime. Now the results I'll present will be in double null gauge, so I'll give a brief review of linearized gravity in double null gauge and talk about how one gets a coercive estimate on 4-dimensional Schwarzschild from the canonical energy in double null gauge. I'll then talk about recent work with Marius Apatorai and Elena Georgi on Reisner-Nordström, and talk about some work in progress for the Schwarzschild-Tangerlini case, or n-dimensional Schwarzschild. Okay, so in general relativity, we work with an n-dimensional smooth Lorentzian manifold, and we require the metric to satisfy everyone's favorite equation, which is the Einstein equation. So this is an equation relating the curvature of the Lorentzian manifold to a matter model that one has to input by hand. So one can set this energy momentum tensor for the matter to 0 to get a non-trivial theory because of the nonlinearities of the left-hand side, and this is known as the vacuum Einstein equation and reduces just to the Ricci flat condition. In this talk, I'm going to be interested in one other matter model, which is electromagnetism, which has an explicit energy momentum tensor constructed from a 2-form given here at the end of the slide. Okay, so the type of equation that the vacuum Einstein equation is obscured by diffeomorphism invariance, but it should really be viewed as an evolutionary equation, and you can see this in harmonic coordinates. So if you require your coordinates to satisfy that box equals 0, then the vacuum Einstein equation has the form of a system of quasi-linear wave equations. And it indeed admits a well-posed initial value problem. So if you give me initial data for the vacuum Einstein equation, you get a unique maximal spacetime up to diffeomorphism invariance. And this was shown in the monumental work of Choquebrahat and Garrosh in 52 and 69. And this is the proper setting to talk about stability, because the nonlinear stability question should be stated in the following form. So if you give me a known solution, then I can ask whether a small perturbation of the initial data for that known solution does the resulting spacetime, which I get from this well-posedness theorem, remain close to or asymptote back to the original spacetime. If so, we would say the spacetime is non-linearly stable. If not, we would have the presence of an instability. This is a very difficult question to address, so a good first step is often to linearize, and all the results I will state today will be in this linearized setting. So what is the linearized vacuum Einstein equation? Well, it results from formally expanding the Ricci flat condition by adding a perturbation, this epsilon h, where h is a symmetric 2 tensor here, and formally expanding the Ricci flat condition to order epsilon. And at order epsilon, you'll get this equation for h. So it couples to the background geometry through the connection for the background and the Riemann tensor here. Okay, and here we have the wave character coming through if we write this as a box. Okay. So for a linear stability statement, we aim to prove that any solution to this linearized vacuum Einstein equation that arises from suitably regular initial data obeys energy bounds and decays sufficiently fast. Then we might have some hope of addressing the nonlinear stability problem. Okay. So how does one get energy bounds typically? So these typically arise from applications of the divergence theorem to currents that one constructs. So if you have a theory on some space-time background, you can often construct some conserved currents when they're divergence free. So a natural construction is if you have some theory that has an energy momentum tensor, you can contract it with a vector field on the spacetime. Now, this will be divergence free when the vector field is killing. Okay? And very formally, one then can obtain energy estimates and indeed conservation laws from applying the divergence theorem to a space-time region bounded by, say, two homologous hypersurfaces. So you would end up with a potential energy to the future, potential energy to the past. Sorry, energy to the future, energy to the past is equal to a space-time bulk. And from this, one can start to derive conservation laws in the case of a vector field that's killing, and potentially energy estimates in the space-time bulk when it's non-killing. Okay, so for example, if you take the wave equation on four-dimensional Minkowski with the killing field associated to stationarity, you have a conserved energy computed from which you can compute from the energy momentum tensor for a scalar field. So you end up with this conserved energy for all the derivatives on, say, a t equals constant hypersurface. Okay. The issue for linearized gravity is that there is no energy momentum tensor, and this essentially boils down to there being no local notion of gravitational energy momentum. You can always take a frame, or you can always take a set of coordinates locally, your normal coordinates, and set the Christoffel symbols to 0. So what's the way around this? Well, this is where the canonical energy comes in. So I'm going to try and motivate this with a simple example with the wave equation and then move on to the more complicated example for linearized gravity, since the expressions are a lot more involved. So suppose I have two solutions to the wave equation. Then I can construct a divergence-free current using a symplectic form on the space of solutions. So you can check that if phi and psi satisfy the wave equation, then this current here is divergence-free. However, this involves two solutions. So if I wanted to get estimates on a single solution, what I could do is plug in for phi the Lie derivative of psi with respect to a killing field, since the Lie derivative commutes through the wave operator. So this is still divergence free. So let's do a small computation together. So if I do this computation and I plug in this solution, which is the Lie derivative of psi with respect to x, and then I expand here with the definition of, sorry, I just expand the Lie derivative and I distribute the covariant derivative over the vector field. I end up with two terms here, which I can then produce a total divergence from this term here after, no, I apologize. Sorry, I can produce yes, I can produce a total divergence and use the fact that x is killing to swap the indices on this vector field, this relation here, to produce a total divergence. And what I can produce in the end is that this current here is equal to the energy momentum current that we can construct from a contraction of the energy momentum tensor into x and the divergence of an antisymmetric 2 tensor. Now this here is always divergence free, since if I apply another covariant derivative to this and then use the infectious nature of antisymmetrization and then the Ricci identity, this term is always divergence free, since you have the contraction of, in the end, the Ricci tensor into A. So then you have that this current here, when we use the Lie derivative of psi in the current, is essentially, up to a total divergence, the standard current that you get from the energy momentum tensor. Okay, and this is the sort of structure that goes through to the canonical energy. So you don't have an energy momentum tensor for linearized gravity, but you do have a current which is based upon symplectic structure. So it turns out that this current here, where P and H are solutions to the linearized equation, and this capital P is just a combination of a particular combination of inverse background metrics. This is conserved when P and H solve the linearized equation. So to start getting a current and doing energy estimates from a single solution, what one can do is the same trick where one plugs in that P is the Lie derivative of H with respect to X, and at this point you might start to obtain a useful conservation law. Okay. However, one of the major issues with this is that when you look at these energies, and I take an extract from Hollins and Wald's original paper on the canonical energy in 2013, the coercivity of this object is opaque. So it's not clear whether one can actually obtain control of a norm from the canonical energy. Okay. One other slight annoying thing about the current form of the canonical energy is that if you plug in that P is the Lie derivative of H with respect to X, you end up with second derivatives in this term here. So it doesn't look like a natural energy norm that you would control. You can indeed modify the canonical energy to get something that is a little bit more natural, which is this current here. So if you are bored in my talk, you can check that this current at the bottom of the slide is indeed divergence free. But this indeed just has first derivatives appearing in the current. So on each, if you evaluate this on a hypersurface, you will just get first derivatives. So it starts to look a bit more like a natural energy that appears. Okay. So I'll give a slightly alternative viewpoint on the canonical energy, but I'll try and review the Hollins and Wald stability criterion. So the canonical energy arises originates from a work of Friedman, but was really popularized in 2013 by this work of Hollins and Wald, and they built a stability criterion based upon the canonical energy. So they took this current and evaluated it on Cauchy hypersurfaces and really came up with a criterion based upon its sign, whether a spacetime was stable or unstable. So for a class of immiscible initial data, and this means that there's no perturbation of the ADM parameters, the linearized constraints are satisfied, there are certain gauge conditions that they're baked into this for finiteness at the horizon and null infinity if one is on a black hole spacetime. And there's a condition of being an axisymmetric perturbation if you're in a rotating spacetime. We have this condition that positivity of the canonical energy is an indication of stability. In particular, you can read off from this that you should be modally stable. Negativity, however, is an indication of instability. And the argument can be viewed in the following manner. So a negative canonical energy implies that a certain modification of it is also negative. And if one is dealing with axisymmetric perturbations or is dealing, axisymmetric perturbations of a rotating black hole, or is dealing with a non-rotating black hole, then you can show that the flux of this modified canonical energy is positive through an event horizon and null infinity. So if it's negative initially, it can only be more negative. So it has a nice monotonicity property, and this is this prevents this is an obstacle to stability. Okay. So I'm going to try and tell you about some more successes in my own work later in the talk, but let me outline some successes from the canonical energy from some previous works. So in the original paper of Hollins and Wald in 2013, they showed that the canonical energy was negative for many black string spacetimes. So in particular, the Schwarzschild black string. So you can infer this as a proof of the existence of a Gregory-Laflamme type instability. There's also the work of Hollins and Ishibashi in 2015, which addressed a conjecture of Durkee and Real for higher dimensional black holes. So they showed that the canonical energy was negative for a class of extremal rotating black holes in higher dimensions. So for some class of Myers-Perry, for example, this theorem applies. There's also the work of Green, Hollins, Ishibashi, Wald in 2016, which showed that the canonical energy was negative for linear perturbations on asymptotically ADS black hole spacetimes, which exhibit superradiance. So this is of relevance, for example, to Kerr ADS. And then there's this work of Prabhu and Wald in 2018, which showed that if you construct a metric perturbation from a Hertz potential, which is a way of producing a metric perturbation from solutions to the Tchaikovsky equation, you get a positive canonical energy. And this is on Schwarzschild. Okay. Now the theory of canonical energy, as I've outlined here, was in vacuum. However, it's been extended and to modified theories of gravities by Joe Keir in 2014. Okay, so let me introduce now the spacetimes of interest in my talk. So this is the Schwarzschild-Pangazzini spacetime. So this is an explicit solution to the vacuum Einstein equation, where I've written the metric in its traditional form. So this is typically viewed as a one-parameter family of massive black holes, where this is the metric that would live on the exterior region. So we have a parameter m, which we interpret as mass. This notation here for this slashed gamma is the notation I use for the standard metric on the n-2 sphere. We have a coordinate degeneracy at r equals 2m to this funny power, which corresponds to the future event horizon. We have a curvature singularity at r equals 0 when we suitably extend. The solution is static and hyperspherically symmetric. So we have a notion of time independence. And it sits as a subfamily of the Myers-Perry family of black holes, or the Kerr family of black holes in 4 dimensions. You can draw a Penrose diagram, which I will use heavily later in this talk, for the maximal evolution of Schwarzschild initial data. Here I've drawn the two-ended version. So here we have an exterior region in light gray, which is bounded to the future by an event horizon, across which is a black hole region, which terminates in the curvature singularity at r equals 0. Note that every point in this diagram is now an n-2 sphere. Over to the right, we have this Scry plus, which is future null infinity, where you should think of as idealized gravitational wave experiments taking place. You can read off causal relations in this diagram by plotting light cones upright, and you can see that you can consider the stability of the exterior region independently of the interior of the black hole, as the interior does not affect the exterior of the black hole. So I can really talk about the stability of the exterior of Schwarzschild, which is going to be of interest later in the talk. Okay. So the other protagonist of the talk is the Reisner-Nordström spacetime. So this is an explicit solution in 4 dimensions to Einstein-Maxwell. Here we have a modification of the Schwarzschild metric with this q squared over r squared term. And we have an explicit Faraday tensor, which is generated through a 1 form, which I've given here in A. So we have a 2-parameter family where the m is now, as before, is the mass, and q is interpreted as the charge of the black hole. We have a coordinate degeneracy at r equals r plus, which corresponds to the future event horizon. We have another root of the horizon polynomial here, which is R minus, and this corresponds to the Cauchy horizon and is the end of the maximal future development of Reisner-Nordström initial data. The solution is again static and it's spherically symmetric, and it's now a subfamily of the Kern-Newman family of solutions, which I think Elena will talk about later in the conference. Okay. So having talked about some previous work on the canonical energy, let me talk about some previous work on the stability problem. Now, there's a vast literature on this stability problem for the Schwarzschild black hole, so I apologize already for not mentioning everyone that should be mentioned at this point. I'm going to highlight some works that are of particular relevance to the results I'll talk about later. So in 4 dimensions, the study of the stability of Schwarzschild dates back to the work of Reggie and Wheeler in 1957, who looked at mode solutions to the linearized equation. This was continued by Zerilli and Vishwesvara in the 70s, but the full linear stability result was resolved in 2016 by de Fermat, Holzigel, and Rudnansky, and this was done in double null gauge, which I will employ today. Another work that came alongside this was a work of Gustav Holzigel in 2016, which studied or produced conservation laws and coercive estimates from the system of linearized gravity in double null gauge, as presented in de Fermat, Holzigel, and Rudnansky. And this is really the inspiration for most of the work that I'll present today. Then in 2021, we have a resolution to the nonlinear stability of Schwarzschild by de Fermat, Holzigel, Rudnansky, Taylor, which is a stability result without symmetry for the full expected set of perturbations. On the Reisner-Nordström side, we have the result of Georgi in 2020 for the linear stability of Reisner-Nordström when Q is less than M, so in the sub-extremal range. And then there is the result of Aperture I in 2023, which produces stability and instability result for the Tchaikovsky system when at extremality for when Q equals M. And I think Marius will talk about this later in the conference. For higher dimensional Schwarzschild, there's a lot less known. There is a mode stability result of Ishibashi and Kodama in 2003, which uses a decomposition into vector, tensor, and scalar harmonics on the n-2 sphere to produce master equations. There's the work of de Fermat and Holzigel in 2010 in symmetry and 5 dimensions, and it's a nonlinear result. In 2013, there's the result of Volker-Schlu, which produces a boundedness and decay result for scalar waves on the background in arbitrary dimension. And in 2018, there is a linear stability result for the master quantities that Ishibashi and Kodama studied. And this is uniform boundedness and decay for these master quantities in dimensions less than 6. So the results I want to present are all set up in double null gauge. So I'm hoping to at least give you some nodding familiarity with double null gauge going forward. So double null gauge is a set of coordinates such that the metric just takes this form here. So we have coordinates u, v, and these theta a's. The level sets of u and v are null hypersurfaces, and these level sets intersect in n-2 spheres. This g slash here is the induced metric on these surfaces, and this b is a vector on these surfaces. It can be viewed as the null lapse, if you like. This omega is a function on n. Sorry, the null shift, and this is the null lapse. I apologize. So this is a function on the manifold. Okay, so what is the idea of double null gauge? Oh, sorry, I'm getting ahead of myself. Let me give you an example. So an example of double null coordinates is on Schwarzschild is the Eddington-Finkelstein coordinate. So if you introduce a tortoise coordinate as so through this differential equation here, this prime is differentiation with respect to r, you can define this u and v as this combination of t and r star. This produces a metric you can check explicitly in double null form with a vanishing shift and a null lapse of the usual Schwarzschild factor with the rescaled R. Your level sets intersect in two spheres of radius R, and your induced metric on those on the two spheres is the standard n minus 2 is the standard metric on the n minus 2 sphere. Okay, so what is the idea in double null gauge? Well, it's to decompose your connection and your Weyl curvature with respect to a null frame. So you define an E3 and E4, which are null vectors. If you plug them into the metric from 2 slides ago, you'll find that they're null vectors. And you have a local frame on these n-2 surfaces. And you decompose the connection, the Weyl curvature, to produce tensors on these surfaces. So for example, you can decompose the connection to produce the shears, these chi and chi bar, and you can decompose the Weyl curvature in the following way, this alpha and alpha bar. And these, for those who are unfamiliar, are the variables that correspond to the Joukowsky variables in the Newman-Penrose formalism. So how do you encode the Einstein equation in this formalism? Well, you decompose the Levi-Civita conditions in this frame, and you decompose the definition of Riemann curvature also in this frame, as well as all the Bianchi identities. So you end up with a huge amount of equations, but for analysis, that's usually pretty good. So after decomposing and linearizing around Schwarzschild-Tangent-Giardini, this is half of the equations. I'm not expecting you to take any of these in, but you can see that some of the Levi-Civita conditions are sitting up here. Some of the Riemann tensor definitions, the definition of the Riemann tensor decomposed are sitting down here, and over here are some of the Bianchi identities. Okay. Now, sitting in this complicated system of equations is actually a decoupled subsystem. So, which actually governs the dynamics of linearized gravity and is gauge invariant. So this is the famous Joukowsky, well, here, system of equations, but in 4-dimension Joukowsky equation. So this is in arbitrary dimension at the moment. You have a coupled system between these alpha and alpha bar and this tau hat, which vanishes in 4 dimensions. So you get a decoupling of this alpha and alpha bar equations. So these equations here are not my own. The n-dimensional case dates back to Durkee and Real in 2011 and Godgazar, but in the 4-dimensional case, it dates back all the way to the 70s, Bardian and Press, Joukowsky, and then Ryan, also in 74. So there's a few issues with the Joukowsky equations. First of all, is an issue already in 4 dimensions. There's no known conserved energy at the level of first derivatives of alpha. So that's a problem from the point of view of trying to do energy estimates. In the Firmus Holzego and Rudyansky from 2016, this was solved via what's come to be known as the Chandrasekhar transformation, which is a second-order differential operator applied to alpha or alpha bar, which takes it to a wave equation with positive potential, which does have conserved energy. The issue in higher dimensions, as you can see already, is that decoupling fails for the Joukowsky equation, and this is happening even on highly symmetric spacetime. So here I've linearized around Schwarzschild-Tangent-Giardini is already a coupled system. I think in this work of Durkee and Real from 2011 that I'm citing, they show that you only get a decoupled Joukowsky equation on spacetimes that are Kundt. Another problem is that there's no known Chandrasekhar transformation for n greater than 4. So one has to think about alternative methods or hope for some transformation to address this problem. So I'm advocating for the former. So this is where the canonical energy comes in. So the idea is to avoid the use of special transformations and special decoupling, and really admit that linearized gravity is a system, and the canonical energy produces a conservation law for this system. The problem with it is that the coercivity of it is opaque, so controlling a norm is difficult. However, there is some guidance from this work of Hosegal in 2016, who spotted remarkably by eye a conservation law for linearized gravity around Schwarzschild.
Sam, can I ask a question?
Yes.
Sorry to interrupt. Yeah, what's the status on mode stability for that system in all dimensions?
So that was solved by Ishibashi and Kodama
It's
for
included in the work for all dimensions?
for the Tchaikovsky system. I don't know if that's been done. That was done it was done from the point of view of linearized metric perturbations.
All right, thanks.
Are there any other questions? No. Okay. So, right. The idea is to admit that linearized gravity is a system and try and deal with the coercivity property. And we have this guidance that comes from Hosegal's work, who spotted remarkably by eye a conservation law for linearized gravity. So in this system of equations, he spotted that you could construct a conservation law. So what's crucial about this is that he also managed to derive a coercive estimate from this, and I'll talk more about this later. But this gives one hope, if connected, that one could produce coercive estimates from the canonical energy. So I've taken a quote from a footnote in this paper from 2016. It is an interesting question whether the conservation law satisfied by the canonical energy can be directly related to the two conservation laws presented in this paper. Okay. So what's this crucial conservation law? So it's set up in the double null formalism, and it lives on a characteristic diamond on the exterior of Schwarzschild. So we have a conservation law that says that the fluxes on this outgoing cone and incoming cone are equal to the fluxes on this incoming cone and outgoing cone. Now these fluxes occur at the level of linearized metric and Ricci coefficients. So this chi bar and chi, eta and eta, these are linearized Ricci coefficients, and we have some linearized metric coefficients appearing in this capital omega 1. Okay. So it has some good terms which are positive, but it also has some terms that look like they're going to be difficult to deal with. So coercivity is still opaque at this stage, but I'll come back to this later. It can be resolved. Right. So let me address the question of whether this is related to the canonical energy. So this goes back to work in my PhD thesis. I sat down and I computed the canonical energy in double null gauge on a characteristic rectangle like this. And the expression is rather horrible, as you can see. So, I mean, it obviously satisfies a conservation law because it arises from a divergence-free current. And this is the expression that one gets. And okay, you sit and stare at this and lose a bit of hope. But if you stare very carefully, you see some of the terms that arise in Hosegal's conservation law are also arising here. So it looks like there is some relation. So what's the resolution? Well, is it related to this conservation law? The answer is yes. And the trick is essentially to spot total derivatives. So if I add and subtract the same quantity on the sphere here and take a v derivative and a u derivative, I can push terms onto the fluxes, onto each flux. So if you do this, and this is a theorem pulled from my thesis, you can show that the canonical energy is equal to, so the canonical energy flux through an outgoing and an incoming hypersurface are equal to the flux that Hosegal writes down on those respective hypersurfaces up to a boundary term on the spheres in the corners. Okay, and those cancel because they come with the opposite sign. So you can show that from the canonical energy, you can deduce this Hosegal conservation law. So I've written it again here. All right. So what about coercivity? So I'm going to present a slightly simplified argument that I deduced with Marius and Elena when we were looking at the Reisner-Nordstrom case. I'll also outline the argument that Gustav and I had, and he had in his original paper for coercivity. But it turns out you can simplify these conservation laws quite considerably if you stare at them long enough. So each flux can be simplified to a shear term and this torsion term and a boundary term. Okay, and I've written the boundary term in a suggestive way. So the first line is good because it's positive. Now one has to just deal with boundary terms. I've written the explicit expressions for x and lambda here. They're not especially important. It's just for concreteness. Something to note, and I've sort of swept this under the rug so far, is about residual gauge freedom. So double null gauge doesn't completely fix your gauge. There are residual transformations which result from refoliating your cones and refoliating the spheres, which one can use to your advantage. It turns out when the fluxes are written in this form, the first line here, these are gauge invariant under transformations adapted to their respective cones. So if I refoliate this outgoing cone, this is actually gauge invariant. Okay. So how does the argument for coercivity go from this perspective? Well, the first step is the same as throughout the years. It's been the same that the original argument goes through. It's a push to null infinity. I take this incoming hypersurface and I push it to null infinity, but I need an appropriate notion of extendability. So the boundary terms that arise, I'm going to write it in a special way, they decay under a suitable notion of asymptotic flatness. So the appropriate definition that comes from Gustav's original paper is that a solution is extendable to null infinity if the following quantities have finite limits as you push v to infinity along each fixed u. Okay, the list I should write for the whole system, but I'm pulling out the relevant quantities here from that list. So under a suitable notion of asymptotic flatness, R lambda is the finite quantity, and it turns out that x is the finite quantity. So this term decays, and this term decays since I have a 1 over r. So it turns out that if if I push the incoming flux to null infinity, I get something that's coercive automatically. So it's just the outgoing flux that one has to deal with. Now, you may wonder how realistic an assumption this is to make, but from the firm of Holzigel and Rodniansky in 2016, one can always normalize my initial data to satisfy this. And these rates, moreover, propagate along null infinity. Okay, so what about the incoming cone? So the outgoing cone. The argument here has changed over the years. So the original coercivity argument depended on gauge transformations. So in Hosegel's original work and our work in 2024, we used the residual gauge freedoms that were adapted to the outgoing cone. So the key quantities that we used were this omega trace chi, the expansion of the outgoing cone, and we noted that the shear was gauge invariant under this quantity. So let me go back to the original, go back to Gustav's conservation laws. Why is this useful? So if you look at this outgoing flux in 13, the shear is gauge invariant under such a transformation, and I can use the expansion gauge transformation to set these last two quantities to 0. So I'm left with one other term. It turns out that if I set the expansion to 0, Varshal-Dury's equation tells me that this middle term is also 0. So you get something that's coercive, but in the wrong gauge. So something that Gustav noticed was that these fluxes were gauge invariant up to boundary terms. And you can essentially see this from the simplified form that I presented on this slide. You can see that these two terms, I told you that these two terms were gauge invariant, and you're left with the boundary term. So it's gauge invariant up to boundary terms. So the original argument for coercivity of the outgoing flux was to look at the difference of to write it in a gauge where the expansion vanished and relate it to the original initial data gauge and deal with the boundary terms that arise from this transformation. And it turned out that that was possible. However, in the simplified setting, one can spot a miraculous transport equation. So it turns out that, and I wrote it in this particular form in the suggested form to highlight this, it turns out that the outgoing flux can be made manifestly coercive. So this term here cancels with this term at the future sphere cancels with its initial data term since it's transported along the outgoing cone. So you end up with something manifestly coercive on the outgoing cone. If you push to null infinity, you get something that's coercive. So you end up with this nice coercive estimate from the modified, albeit modified canonical energy. Okay. So there is a failing here, which is interesting if anyone is wanting to explore, is that the analogous argument where one pushes to the horizon first and tries to make the incoming flux manifestly coercive fails. The signs conspire against you, and I've thought about this for a long time, but I cannot make it work. So there's something to try and understand here. It could be that the structure of null infinity is essential here. Okay. So how far can you push this? I've only got a partial energy boundedness result here. How far can you push this? Well, it turns out that you can get control on the Tchaikovsky variables from these conservation laws. So this is the main theorem from our paper from 2024. If you give me a smooth solution to linearized gravity on the Schwarzschild exterior, we can estimate in terms of uniformly bounded initial data all tangential derivatives to the outgoing cone. We can actually get all derivatives just because there's a Bianchi identity for this of alpha, and we get all tangential derivatives of alpha bar, although with some degeneration, although one might expect that if you invoke the Tchaikovsky equation and do a redshift estimate, you can improve this. So how does this work? So I'll give you the essence of it. You can commute these conservation laws with the symmetries of the Schwarzschild spacetime. So with the SO3 killing fields and DT. So for example, if you wanted to get control over alpha, you would look at the commuted canonical energy conservation law with DT. Okay, and so you get control over DT of the shear. You have this already appearing in the first canonical energy conservation law. It turns out with some transport estimates, you can get control over the other quantities as well. And what's nice about this, and why I think this is really well adapted for studying higher dimensions, is that it doesn't require a transformation to the a Reggie-Wheeler equation, and it doesn't even require analysis of the Tchaikovsky equation itself. So you don't have to invoke any decoupling, for example. This just comes through figuring out a hierarchy that sits in the system of linearized gravity. Okay. I have 15 minutes, is that right?
Yes.
Okay. So let me skip through putting Reisner-Nordstrom in double null gauge. Let me just say, you can put Reisner-Nordstrom in double null gauge and also do the linearization around Reisner-Nordstrom. You have extra quantities associated to the Maxwell field, which you have to decompose with respect to this null frame. So you have this rho f, sigma f, beta f, and beta bar f. And you have a coupling between gravitational electromagnetic quantities through Q. So you can see here that this is after linearization around Reisner-Nordstrom. You have coupling of the Maxwell quantities to here, for example, is a linearized connection coefficient. And the same thing happens in the linearized Bianchi identity. So one has to really deal with explicit coupling. However, the conservation laws, and this is what Marius and Elena and I figured out in 2025 go through quite cleanly. So the modified canonical energy conservation law on the exterior of Rosen-Nordstrom can be stated in quite a clean and simple form with a slight modification from the Schwarzschild case. So you get three extra terms here in the middle. So the Schwarzschild conservation law is just these last two. You end up with three extra terms for the Maxwell part, which all contribute positively. The issue that I'll talk about is with the boundary term. Okay, so how does the argument go here in the Maxwell case? So the outgoing, sorry, pushing the incoming flux to null infinity goes through just the same as in the Schwarzschild case. It turns out that these terms here decay sufficiently rapidly so that you get something coercive when you push to null infinity. The issue arises for the outgoing cone. So we have a partial result for this. So I'll try and explain where this comes from. So we get a coercive estimate for Q less than or equal to root 15 over 4m. And this essentially arises from these two terms here. So if you remember in the Schwarzschild case, this term was transported, so you could cancel the future sphere term with the initial sphere term. Unfortunately, in Rosen-Nordstrom, this term is no longer transported. It actually it produces essentially this rho f term that sits here. So one might hope that you can do some estimate and recover coercivity up to and potentially including extremality, but this fails before extremality. And the reason is the reason one can spot is the reason one can see through is the following estimate. So if you compute from the linearized equations the dv of this square here, which tends to this red term here, you can see that it produces this rho f term. So I can add this on, I can add 0 effectively in this form to this conservation law and try and cancel this term in red. Or more naturally, what I can do is I can add this quantity on the right-hand side to the flux and get a quadratic form in x and rho f. And in the boundary term, I can get a quadratic form in x and lambda. Okay? And if you look at Sylvester's criterion, which gives you a set of necessary and sufficient conditions for positive definiteness of a quadratic form, you find that this works up to and including works for charges up to and including root 15 over 4m. Okay? And so here there's work to be done. It's unclear whether one can produce an estimate which absorbs it into, say, some of the other Maxwell terms or some of the other gravitational terms. But in some sense, we have an optimality result in terms of how much can be absorbed in terms of this rho f term. Okay. Again, one can push this quite far and gain control over the Tchaikovsky quantities, which there are now 3 of them for Einstein-Maxwell around Mersenne-Nordstrom, and this was identified by Georgi in 2020. So you have combinations that are gauge invariant in addition to alpha and alpha bar, which satisfy Tchaikovsky type equations. And you can again gain control over all tangential derivatives along the outgoing cone in terms of a uniformly bounded initial data energy. Okay, so everything goes through up to, but not including, charges of, there's a typo here, this should be root 15 over 4. We lose the equality here because at the equality of root 15 over 4m, we lose control over many of the quantities. So we can't push the hierarchy we constructed. Right, so let me talk a little bit about work in progress. And I've thought about this for many years and it's still in progress. So what about higher dimensional Schwarzschild? So I think it's particularly well adapted, the canonical energy method, to think about higher dimensional Schwarzschild, because it doesn't rely on any decoupling of the Tchaikovsky equation, and it doesn't require transformations to some Reggie-Wheeler variable. So the conservation law can again be written in a fairly simple way. So the conservation law looks like it does in four-dimensional Schwarzschild with an additional term which includes the Ricci curvature of the perturbed spheres. And the boundary terms are almost exactly the same up to dimensional factors. It turns out that if you make a suitable notion of extendability to null infinity, the incoming flux is coercive when you push it to null infinity. And what I think is the suitable notion of extendability to null infinity is taking the values in 4 dimensions and raising them by half a power for every dimension you increase. These rates propagate along null infinity. The issue that arises again the outgoing flux. So, as happened in Reisner-Nordström, the transport of the natural quantity in higher dimensions fails. So it's proportional to the double divergence of the shear with a dimensional factor which makes it 0 in 4 dimensions. So if the shear is divergence free or it's constructed from a covector potential, this vanishes, so you have a transport equation. There's another additional issue, and it's the reason why I didn't write it in any suggestive form on the previous slide with a difference of squares, is that this x quantity, as I've written it in higher dimensions, doesn't have a regular limit towards null infinity. So there's 2 issues with the boundary term that one has to deal with. Another puzzling issue is also that, well, is this mixed term between the Ricci curvature of the perturbed spheres and the shear. So you can exchange it doing this trick with total derivatives to a term which is a quadratic form in the linearized metric on the sphere and its angular derivatives. This is positive, definite when it's sourced when this linearized metric is transverse or sourced by a covector potential, but is negative definite when sourced by a function. So if you construct it through 2 angular derivatives of a function, it has the wrong sign. So there's something to be understood here in terms of decomposition. There is some hope that one can rectify this with an additional conservation law, which is novel in more than 4 dimensions. I won't present it here. It's also very complicated and not particularly enlightening, but it does give control over this perturbed Ricci curvature in higher dimensions, or it could give some control, I should say. It does. I've not proved it does. Okay, so that's the status of the higher dimensional case. It seems promising, but there are lots of pitfalls that one has to deal with. So what about the outlook for the canonical energy? Well, an interesting question is looking at axisymmetric linear perturbations of Kerr, and this should yield to this technique, but one maybe has to be a little bit careful about the decomposition that one uses. I, at some point, did the computation in double null gauge, and it gives a very complicated expression, which is difficult to read off coercivity from, but maybe one can find the correct gauge invariant variables and write it in this way, as I did in the Schwarzschild case. It's certainly an interesting problem. The process that I've highlighted so far very much exploits this notion of extendability to null infinity. So I've thought a lot about trying to push to the horizon first and have failed in the attempt. So it seems like this definition seems somewhat necessary to make this work, but not to say that one can't push the horizon first, but it's an interesting problem to explore. And relatedly, what can one do with different asymptotics? If you took Schwarzschild ADS, what can one do in this case? Anyway, I think I'll end here, and thank you for listening.
Dimensions. So it will be a very right and soft presentation, so you can relax and stop me any time if you have any questions. Okay, so we start with recalling some very well-known things about 3+1 dimensional black holes, and then recall some results about stability of black holes, both as solutions to the vacuum Einstein equations. And I will also consider a particular matter model, which is the Einstein-Vlasov equations. In the second part, I will then present to you some higher dimensional black hole solutions and try to tell you a little bit about what we know about the stability, what we expect about the stability of these solutions. And I will try to also tell you how one can start by studying linear fields on these fixed black hole backgrounds and then try to understand more advanced and complicated stability properties of these solutions. So among higher dimensional solutions, I will focus on the case of 4+1 dimensions. So just one dimension higher than the usual black hole solutions that you all know. Okay, so we are interested. I should also say that everything I'll say will be classical, and I will restrict to the case of zero cosmological constant. Okay. Okay, so we're interested in the stability of the black hole exterior as a solution to the Einstein equations that you see on the slide. And let me remark that these equations can be formulated in dimension greater or equal than 3+1. So for me, n will be the total, the full space-time dimension in the rest of the talk. So as Soon-Jin reminded us at the very beginning of the conference, the Einstein equation admit a locally well-posed initial value formulation, which provides the mathematical framework to study the dynamics of solutions from the point of view of evolutionary PD. So if you want, for an evolutionary PD perspective. Okay. Now let me start by looking at the special case where the energy momentum tensor T is identically vanishing and the equation reduced to the vacuum Einstein equation reaches equal to 0. So as we all know, that meet explicit stationary asymptotically flat solutions that I list on the slide. So the simplest solution is the trivial one, the flat solution called Minkowski space that was originally formulated by Minkowski in the context of special relativity. The simplest Yes. There's a green light, so I can assume green light, assume it's on. Simplest non-trivial solution is Sfacci solution formulated right after the original formulation of general relativity by Sfacci in 1916. And then we have a more complicated geometry called the Kerr solution, discovered much later in the 60s in 1963. And we know that one very interesting property of Sfacci and Kerr is that they describe black hole solutions. So I'll very quickly recall some properties. This is the Sfacci solution in Sfacci coordinates. Sfacci solution is really a one-parameter family of black hole solutions parameterized by parameter m, which I will call the mass and assume will be greater or equal than 0. This is a family of static, spherically symmetric, and asymptotically flat solutions, which embed as a dm equals 0 member of the family in Minkowski space. And let me also recall a remarkable, important property of the rigidity property of this family, namely the fact that any spherically symmetric solution to the vacuum Einstein equations is isometric to Sfacci solution for some m, for some mass m. In particular, this implies that spherically symmetric or spherical symmetry implies no dynamics in the vacuum case. Okay, and this goes under the name of Birkhoff's theorem. Now, the Sfacci family sits within a wider, more general family of rotating black holes that is called the Kerr family. And again, the metric is explicit. You see here on the slide. It's a two-parameter family of black hole solutions with parameters A and M. The Stoker will take A in the subextrema range strictly less than M. So this describes a family of stationary axisymmetric black holes, which are again asymptotically flat. And for A equal M equals 0, the matrix formally reduces to Minkowski space. And the family embeds the Sfacci family as the A equals 0 one parameter subfamily. Here, again, there is a rigidity property, which the way stated on the slide, it is a conjecture. The n is smooth stationary and asymptotically flat solution to the vacuum Einstein equation is isometric to curve spacetime for some A and M. Okay. Now let me recall the very few some of the nonlinear stability results that we know about these solutions. So the nonlinear stability of Minkowski space, again, we heard about this in Sunjin's talk, was originally proven by Christodoulou and Kahneman in the 90s. What about black hole solutions? So it turns out that with very few nonlinear stability results for black holes, in the A = 0 case, meaning in the Schwarzschild case, there is a proof of nonlinear stability of Schwarzschild by the Fermat-Sozeger, Rodinsky, and Taylor, which characterizes all small vacuum perturbation on the given Schwarzschild solution, which eventually converges to a possibly different Schwarzschild solution. So let me remark that if you consider a general small perturbation of Schwarzschild, you expect that the evolution of the perturbed data will converge to a slowly rotating curved black hole with mass similar to the original mass of the Schwarzschild black hole. So in this sense, the problem of nonlinear stability of Schwarzschild has, in a sense, to be understood already within the curve family. And because of the rigidity result that I mentioned before, Birkus theorem, the problem also has to be understood when in vacuum. It has to be understood outside of spherical symmetry or any other 1+1 dimensional reduction. I would also like to mention previous work by Kahneman and Sheftel in polarized axis symmetry, which is a 2+1 dimensional reduction of the nonlinear stability problem for Schwarzschild. In the slowly rotating regime, there's a series of papers by George Kahneman, Sheftel, and Shen proving nonlinear stability, whereas the full resolution of the nonlinear stability problem in the full subextrema range remains to be done in future works. So in the next slide, I'll summarize quickly the steps of works that led to these results that you see on this slide. But before moving to that, let me emphasize that the curve metric can also be considered in the so-called extremal case, where A is equal to M, which one expects a very different picture from the one that I alluded to in this slide, which is as interesting as the one that I'll be describing in the subextremal case, and about which you will hear, I think, in talks and also in the last analysis lecture, if I understand correctly. Okay, so this gives me the opportunity to sort of move to the next slide about the subextremal case. So this is, if you like, a very condensed presentation of what has been the roadmap towards the understanding of this stability problem. It's a body of works from the 60s and 70s from the physics literature on the linear mode stability of black hole solutions, in which, together with showing linear mode stability, there also present some ideas and insights that remain very central in our more modern and today's more mathematical approach to the problem. And I'll mention one in a minute. However, to prove nonlinear stability of this solution, one needs a more thorough understanding of linear stability. So the first step, one can look at the wave equation on fixed black hole backgrounds and prove decay for general solutions to the wave equation. And I've reported here some contribution towards this problem. There's also been works about the precise asymptotics of waves on black holes, which also are interesting. And I've only sort of mentioned, again, some of these works, but there are many others that I'm not mentioning here. The second step is understanding solutions, black hole solutions, stability of black hole solutions as solutions to the linearized Einstein equations. And I've reported here some works. I want to recall that most of these works, they build upon an idea which is actually presented in Tarkovsky's work, namely the fact that the system of linearized Einstein equations can be formulated in such a way that two of the linearized quantities present in the system, which are in fact linearized curvature quantities, they're gauge invariant and exactly decoupled into two wave-like equations, which are called Tarkovsky equations. So this gives you the opportunity to analyze these two quantities separately from the rest of the system, But then to apply linear stability result to the nonlinear problem, you also have to control and approach the rest of the system and control the gauge-dependent quantities in the system. So this is sort of the complete linear stability problem for black holes. So together with these linear models, another interesting model is that of studying nonlinear waves on fixed black hole backgrounds. So there are works also in this area. Here I've only mentioned a very recent one about the Fermi-Osogek-Rodiansky and Taylor looking at quasi-linear waves on fixed curve backgrounds in the full subextrema range. Okay, let me emphasize again, there are many more works than the ones I've stated on this slide, but because I want to get to the high dimensional case, I will sort of leave you with these references. Okay, so this was the case of the Einstein vacuum equations. Now I want to say something about the Einstein-Vlasov equations. And there will be a non-trivial overlap with Jacques that I should thank. And so you see a summary of what Jacques explained in a more sort of detailed way. So the Einstein-Vlasov equations, they govern relativistic collisionless many particle systems. And they are formulated like the system that you see on the slide. So you have the energy, you have the Einstein equations with energy momentum tensor. When the energy momentum tensor, you see F, there is a non-negative distribution function which depends on position and momentum variable, and this transported along the geodesic flow of the manifold Mg, as encoded by the relativistic Vlasov equation, which is the third equation appearing in the system. So X is the generator of either the null geodesic flow of Mg, and this will give you the massless Vlasov equation, or the generator of the time-like geodesic flow of Mg, and this corresponds to the massive Vlasov equation. Okay? Solution to Einstein-Vlasov system is a triple Mg-F, and in particular, the stationary vacuum solutions that I showed you in one of the previous slides, so Minkowski, Schwarzschild, and Kerr, they solve coupled with a trivial F, meaning F identically vanishing, they solve the Einstein-Vlasov equations. But now in the massive case, and this again was said by Jacques already, so in the massive case, it turns out that there exist non-trivial, meaning solutions with non-identically vanishing F, non-trivial static spherically symmetric black hole solutions to the Einstein massive Vlasov equation bifurcating from Schwarzschild spacetimes. So this is due to Rhine and Jabiri. So these are in fact smooth solutions where F is compactly supported. So similarly, it happens for Kerr spacetimes. So there exist now stationary axisymmetric black hole solutions to the Einstein massive Vlasov equations bifurcating from Kerr spacetimes. Okay, let me note that in fact, for the massive Vlasov equation on fixed Schwarzschild spacetime, already admits an infinite dimensional family of non-trivial stationary solutions. So this again was said by Jacques. So the behavior, of course, the Vlasov equation being a transport equation along the geodesic flow, the behavior of solution is very much dependent on the geometry and the structure of the geodesic flow. And in particular, the existence of the stationary solutions to the massive Vlasov equation on Schwarzschild is due to the presence of bounded time-like geodesics that do not cross the event horizon. Okay, so in particular, for increasing values of the conserved angular momentum of the geodesic, you can find a curve in the radial potential governing the radial motion of the geodesic, which allow for bounded sort of motion around the local minimum of the potential. Okay, so this I'm drawing is the potential, the radial potential for time-like geodesics for the Schwarzschild spacetime. Particle mass 1, so the potential is asymptotic 1. Okay, so this should be put in contrast with the massless, in the case of the massless, or if you want the null geodesic flow, where the potential can only admit a local maximum, and you have this phenomenon that we typically call unstable trapping. And the Einstein massless Vlasov equation, they do not admit these bifurcations of this type that I describe on this slide. Nonetheless, there exist sort of large data deviations from Schwarzschild spacetimes, if you like, which give rise to static solutions to Einstein massless Vlasov equation, and this is due to some works by Andrew Hanson. But this won't be sort of directly relevant for what I'll be saying before. Questions? No questions. Okay. Now, crucial. Let me go back to the stability problem and summarize what is known about the stability of stationary solutions to Einstein-Vlasov. So in the case of Minkowski space, there are results by spherical symmetry by the Fermons proving nonlinear stability of Minkowski space as a solution to Einstein massless Vlasov. And later independent works by Taylor and Bigorn, Feynman, Judius, Mulevich, and Thaler proving nonlinear stability outside of symmetry. In the massive case, there's work by Ryan and Randall in spherical symmetry, and later work by Lindblad, Taylor, and Feynman, Judius, Mulevich, who independently prove nonlinear stability outside of spherical symmetry. Now, what about the Schwarzschild solution? So stability, the only nonlinear stability result known for this solution is this work by Veloso and Ruiz that Jacques sort of alluded to in his talk, in spherical symmetry, proving nonlinear stability of Schwarzschild as a solution to the Einstein massless Vlasov equations. Okay, and here in this picture, one expects stability even outside of spherical symmetry. Now, on the other end, because of the existence of these stationary solutions that I mentioned before, non-trivial stationary solutions that I mentioned before, one expects that in the Einstein massive Vlasov case, the picture is much more complicated, and in particular, you can only hope to converge to one of these non-trivial stationary solutions via a more complicated mechanism than the stability mechanism that you would observe in the massless case. And this has to do with this mixing phenomena that Jacques described in his talk. Okay? And let me again mention this work by Chaturvedi and Luke for the non-relativistic case for the Vlasov-Poisson system, where they that you may view as a sort of non-relativistic analogy pointing towards the understanding this problem here in spherical symmetry, if you like. Okay. Now, a crucial ingredient in the understanding of the nonlinear stability of Schwarzschild as a solution to Einstein-Vlasov is the study, is sort of understanding decay for the Vlasov equation now as a linear equation on a fixed Schwarzschild spacetime. So here I want to summarize results in this direction. So in the massless Vlasov equation, there are works by Weissenbacher, Veloso, Ruiz, and Bigogni, Veloso, Ruiz proving decay to zero of the energy momentum tensor associated to F. So here, remember, the Vlasov equation is a transport equation, so F will be transported along the geodesic flow. So the natural quantity for which you want to show decay is the energy momentum tensor or components of the energy momentum tensor. And in these works, exploiting the unstable nature of the null geodesic trapping, they show exponential in time decay for the energy momentum tensor. Let me also mention work by Anderson, Blue, and Jodieu proving a degenerate integrated decay estimate in the case of slowly rotating curved spacetimes for the massless Vlasov equation. And there is upcoming also work by Bigogni and Veloso Ruiz studying the massless Vlasov equation full subextremal curved spacetimes. Now, in the case of the massive Vlasov equation is different, again, because of the existence of stationary solutions. One in general does not expect a general decay statement for solutions. There is results by Veloso Ruiz proving decay to zero of the energy momentum tensor for dispersive F, meaning for the largest family of Vlasov fields F, which are not supported on those bounded time-like geodesics that I referred to before. Or if you want, conditionally to the fact that T, the energy momentum tensor associated to F, decays to zero. Okay? So let me comment maybe on this. So here the results shows decay, polynomial decay in tau, and this decay rate sort of rises. So it's lower than the Minkowski rate for the massive Vlasov equation on Minkowski, and it arises by the existence of geodesics which can travel away from the event horizon for arbitrarily long time before turning back and crossing the event horizon. So in particular, this can really be understood as a decay rate in a bounded area region. So you see this effect already in a bounded area region on Schwarzschild. Okay? So this phenomenon is sometimes called parabolic trapping. Okay? And it is the one determining this rate that you see here. And let me also mention this series of works that also Jacques mentioned in his talk, where they analyze and they study the dynamics of Blasov fields, which are now supported on this bounded time-like geodesics around the minimum of the radial potential. Okay. So this was my review of the 3+1 dimensional case. Questions? Okay. So let's move on to the higher dimensional case, which would be, for today, would be 4+1 dimensional. So the Einstein vacuum equations in higher dimensions, they govern higher dimensional general relativity, which is, it seems to be of some relevance for theories of theoretical physics, which are formulated in higher dimension and for which you need to embed to gravity. They admit, as in the case of 3+1 dimension, they admit explicit stationary asymptotically flat solutions. So as you will see, all these solutions that I'm listing, they're all explicit matrix that one can really write down. So again, you have a high-dimensional version of Minkowski space and a high-dimensional version of the Schwarzschild solution that is called Schwarzschild-Tangerlini solution that is due to Tangerlini from 1963. So this is a direct generalization of Schwarzschild. You have a Kerr high-dimensional version of Kerr black holes that are called Myers-Perry solution, Myers-Perry black holes. They were first formulated in the 80s in 1986 by Myers and Perry. And then there is a new completely independent family of black holes, which has no lower dimensional correspondent version, which is called the family of black rings. It's originally discovered by Emparani and Reali in 2002. So Schwarzschild, Tangerlini, Myers-Perry, and black rings, these are all black hole solutions and are the black hole solutions that I will talk about, excluding for today's talk, the last family of solution, black rings. Find them very interesting, but for today, I would like to say something about the other ones, okay? Okay, so very quickly, this is Schwarzschild-Tangerlini, metrical Schwarzschild-Tangerlini solution. This we saw in Sam's talk. Again, one parameter family of static, spherically symmetric, and asymptotically flat solutions. For m equals 0, you recover back Minkowski space. So I'll be looking, so you see that here you can really formulate for any dimension higher than 3+1. Okay, so again, as in the 3+1 dimensional case, there is a high dimensional version of Birkhoff's theorem that states that any spherically symmetric solution to the vacuum equation is again isometric to a Schwarzschild-Tangerlini solution for some mass. So again, spherical symmetry, even in higher dimensional, implies no dynamics. Implies that you are static. So the Schwarzschild-Tangerlini family sits within this more general family of rotating Myers-Perry solution that is now a 3-parameter family of solutions, where the parameters are called A1, A2, and M, which satisfy this sub-extremal relation, sub-extremal range, which are slightly simplified from the actual one, but we won't lose any information from looking at the relation in this way. So A1 plus A2 is strictly less than M. So this is a family of stationary black hole solutions with spherical topology, meaning that, for instance, the intersection of a Cauchy hypersurface with the horizon will be a topological 3-sphere. So it's a spherical black hole solution. It is biaxially symmetric. So now in 4+1 dimensions, solutions cannot meet 2 independent axes of rotation. And the solution will be symmetric relative to both the axes. They're asymptotically flat in the usual sense that you know. So in particular, if you set A1, A2, and M equal to 0, you recover 4+1 dimensional Minkowski. And the case A1 equal A2 equals 0 corresponds to the 1-parameter family of 4+1 dimensional Schwarzschild-Tangerlini solutions. So here you see on this diagram, you see the allowed black hole parameters. So in particular, let me stress that, so this point corresponds to the Schwarzschild-Tangerlini solution. So these regimes will be singly rotating. The ones on the axis will be singly rotating regimes, where one of the two angular momenta is equal to 0. There's another special regime that in some cases sort of simplifies the problem a lot, which is the one of equally rotating Myers-Berry black holes, let's say, where A1 is equal to A2. And this line will be the extremal members of the family. Okay, and the area, if you like, is fixed by the mass of the black hole, the area of this sort of triangle. Okay, now contrary to the case of Kerr black holes, there's no rigidity conjecture precisely because we know about the existence of black rings, okay, which are independent from this family. Okay, now let me get into stability of these black holes. So there's only one nonlinear stability results for what concerns the vacuum Einstein equations for higher dimensional black holes. And this is very early work by Olszagel and then the Fermos-Olszagel that proves nonlinear stability of the Schwarzschild spacetime as a solution to the Einstein vacuum equations in 4+1 dimensions. So this is a problem done under a 1+1 dimensional symmetry reduction in a symmetry class, which is more general than spherical symmetry and which allows for two dynamic degrees of freedom. Okay, sometimes called biaxial Bianchi knife. So other than this result, there's no other nonlinear stability results for higher dimensional black holes to the best of that are known, or to the best of my knowledge. So the expectation is that Myers-Berry black holes as solutions to the vacuum Einstein equations, they would be nonlinearly stable, again, as solutions in the vacuum case. Whereas what I will try to explain today, perhaps one should expect that the dynamics of Myers-Berry black holes as solutions to the Einstein massless Vlasov equation will again be similar to those of Kerr black holes. But on the other hand, in the case of Einstein massive Vlasov equations, there will be some significant differences. And this would arise already in the case of higher dimensional Schwarzschild. So in the case A1 equal A2 equal to 0. Okay. So as a preliminary step towards understanding sort of these two comments and these two problems, it is, as it was done for Kerr black holes, one wants to start by understanding decay for linear fields on fixed Myers-Berry black holes, for which very little is known if compared to the problem of Kerr black holes. Questions? Okay. Now, before moving to considering some linear fields and telling you what one really wants to understand, I have a slide about the geodesic flow of higher dimensional black holes. And this really will be, I think, the main slides of the sort of the main idea of the talk, the main slide of the talk. So like in the case of Kerr black holes, the geodesic flow of Myers-Berry black holes, it is completely integrable. Okay, so you can, in particular, separate and study the radial motion as a one-dimensional problem, if you like. Now, here are two important properties of the geodesic flow. So all Myers-Berry black holes admit no quotation mark stable trapping of null geodesics. So this means that, like in the case of Kerr black holes, the radial potential corresponding to null geodesic motion can admit at most one critical point, and this will be a local maximum of the potential. Okay, so this is like in the case of Kerr. The second property is in contrast with Kerr, and it has to do that now in the case of time-like geodesics, again, the potential can admit at most one critical point, and this critical point will be a local maximum of the potential. So in other terms, you cannot have any stable trapping of time-like geodesics in the case of Myers-Berry black holes. Is it clear? Yeah, okay. And this already sort of arises, as you can already see, in the case of higher dimensional Schwarzschild. So the picture that you see here is for 4+1 dimensional Schwarzschild black holes, the plot that you see, where for zero angular momentum, if you like, you will have a curve like this, asymptotic 1. For increasing conserved angular momentum, you will have these gray curves that you see on the picture. And then for the angular momentum above a certain critical value, you will have the top curve that you see in the plot. So you only have one critical point that will be a local maximum. Okay, so if you forget for a second about Myers-Berry black holes and we only think about higher dimensional Schwarzschild, these properties remain true for any higher dimensional Schwarzschild black hole. But one sort of curiosity about the number of dimensions, which I didn't appreciate before, is that in the case of n greater or equal than 5 plus 1, meaning starting from 2 dimensions higher and above, the only geodesics which do not have a critical point are those with L equals 0. So for any positive L, you will have a curve like the one that you see on top. Okay? Okay. So now, what I want to explain is sort of how this ingredient and this sort of property affects and sort of contrast with the properties of linear fields on these black holes as compared to curve, or to Schwarzschild, if you like. So first slide would be about the Vlasov equation. So again, we want to look at the Vlasov equation on fixed Myers-Berry black holes and prove decay. Now, in the case of the master's Vlasov equation for Schwarzschild, meaning A1 equal A2 equals 0, there is upcoming work in collaboration with Flavio Rossetti, where we prove decay to 0 of the energy momentum tensor with an exponential rate. So this, if you like, both the nature of the statement and the properties that you exploit will be very similar to what you see for the 3 plus 1 dimensional Schwarzschild case. And there is ongoing work by a graduate student at GSSI, graduate student of mine, Anja Lauri, where she looks at the case of the master's Vlasov equation, but now on Myers-Berry black holes. Okay? So here again, let me stress, in this picture, you expect something similar to the curve picture. Now, in the massive case is where you see a difference. So in the case of A1 equal A2 equals 0, so 4 plus 1 dimensional Schwarzschild, in upcoming work with Flavio, we prove unconditional decay to 0 of the energy momentum tensor. So here, because of the absence of these bounded time-like orbits that were present in 3 plus 1 dimensional Schwarzschild, one doesn't have to worry about the presence of stationary solution to the massive Vlasov equation. Okay, so in particular, you can prove an unconditional result without having to restrict to the dispersive Vlasov fields, okay, without having to restrict to the solutions that you consider. So in particular, we prove a polynomial decay of the energy momentum tensor that you see on the slide, where the exponent of, if you like, the rate of decay, it depends on the concavity of this parabolic trapping of this curve that I showed you before on the slide. So that's where arises the dependence on the number of dimensions in the decay rate. Okay, whereas the case for Myers-Berry black holes remain perhaps for future works. And again, in the future, one maybe wants to understand how this different picture in the massive case that already arises for the massive Vlasov equation on fixed background, how this enters maybe in the nonlinear problem already for the stability of high dimensional Schwarzschild as a solution to the Einstein massive Vlasov equation. Okay. Do you have any questions? No questions. Okay. Now, let me also, for completeness, to tell you something about the wave equation. The wave equation, like in the case of curved black holes, is fully separable on Myers-Berry black holes. And there are very few results known about linear waves on Myers-Berry black holes. There's 2 papers about high-dimensional Schwarzschild black holes by Schlue and Laut-Metcalfe proving polynomial decay for the wave equation on high-dimensional Schwarzschild. And there is another result by Laut-Metcalfe, Tikar and Toneanu proving an integrated decay estimate on slowly rotating Myers-Berry black holes. So this would be Myers-Berry matrix close to the origin of this plot that I showed you before. And then there is a mode stability result, which is quite recent, for the wave equation in the full sub-extrema range. Okay, so like in the case of Kerr, here one expects that one expects uniform boundedness and polynomial decay for general solutions to the wave equation in the full sub-extremal range of Myers-Berry black holes. And let me also emphasize that maybe understanding the Masters-Vlasov equation on these spacetimes may be viewed as sort of an intermediate or preliminary step towards then maybe studying the more complicated wave equation. Okay. Now, last slide. It's about the Maxwell equations on Myers-Berry black holes. So the Maxwell equations can, in a way, be understood as a intermediate step between the wave equation and the linearized Einstein equations, in that you now dealing, instead of dealing with a single scalar equation like for the wave equation, you now deal with a system of linear equations. Okay, so the Maxwell equations can be formulated as a first-order system for components of the Maxwell tensor F relative to a certain null frame that you would have to choose on Myers-Berry black holes. Now, I claim that there is a convenient choice of this null frame on Myers-Berry black holes that is called the algebraic special frame of Myers-Berry black holes, which has a Kerr analog, which I'll describe in a minute, and relative to which you can define your Maxwell unknowns, alpha, alpha bar, rho, and sigma, as you see on the slide, and understand these unknowns as tensors over the orthogonal complement of the span of E3 and E4. So this would be the horizontal distribution over which these quantities are defined. And it is a property of this algebraic special frame that this distribution on which you define your unknowns will be a non-integrable distribution in the sense of differential geometry, meaning that the commutator of the basis of this distribution won't be closed under commutation of the vector in your basis. Okay, so this is something that you can also do and has been done on Kerr spacetimes, where you can choose the algebraic special frame of Kerr to define your Maxwell unknowns. And again, you run into this complication of having to deal with horizontal non-integrable distribution, but now gaining at the advantage of the following property, namely the fact that the two extremal Maxwell components, alpha and alpha bar, they will decouple from the rest of the Maxwell system and satisfy the spin ±1 Tarkovsky equations, which you can then analyze independently from the system, and then go back to the system and control rho and sigma, exploiting your prior control on alpha and alpha bar. Okay, and this is somewhat the approach followed in these two works that I mentioned here by Pasqualotto and Teixeira da Costa and myself in the Schwarzschild and full sub-extremal Kerr cases, respectively. There are also other works exploiting this idea in the Newman-Penrose language as well. On the other hand, by formulating the system in this way, for the Maxwell equations of Myers-Berry black holes, one will have to dispense with the Tarkovsky decoupling for alpha and alpha bar. So it is known, and this was actually briefly mentioned by Sam in the previous talk. So it is known that even relative to the algebraic special frame, already in the Maxwell case, the extreme Maxwell components, they do not decouple into spin 1 Tarkovsky equations. Or in fact, they do not decouple into any decoupled equation from the rest of the system. Okay, and this was observed in the language of Newman-Penrose quantities, was already observed in these works by Godazar and Darky and Rial. These were mentioned by Sam as well. Okay, so in the case of A1 equal A2 equals 0, so in the Schwarzschild case, so it turns out that there is still a residual, here I call it a Faccarelli-Ipser type decoupling of rho and sigma. So there is a residual decoupling of the two middle components, which can in fact be decoupled into two separate wave-like equations and analyze separately from the rest of the system to then go back to the system and control alpha and alpha bar. And this is what is done in upcoming work by Pierfrancesco Martini, who's also a graduate student at JSSI. In the case of Myers-Berry with A1 and A2 non-zero, one also has to dispense with this residual residual decoupling of rho and sigma. So now it's really the case that none of the quantities appearing in the system will decouple from the rest of the system. Okay, so there is something more that one has to understand, and this is subject of ongoing work by Pierfrancesco. Okay, so the failure of this Tarkovsky decoupling will persist in the case of the linearized Einstein equations. So if you like, this Maxwell problem is, in this sense, sort of a step to then maybe understand the failure of this decoupling in a more complicated case of the Einstein equations. And in the case of high-dimensional Schwarzschild, sort of this residual decoupling of the middle quantities in the Maxwell case as a reflection in the decoupling of some quantities into Reggie-Wheeler type equations in this work by Keller and Wang about the linear stability of high-dimensional Schwarzschild black holes. Okay, so this is all I wanted to say. I think I went. Do we still have 10 minutes?
Yes.
Okay.
With questions.
Maybe I can take questions, and then if I have sort of some more time left, I will say something more. Okay.
Let's take questions now.
How much time do I have?
I mean, totally have another 12 minutes, including.
Okay. Okay. So then I have one more slide about yeah, I don't remember if it's supposed to be 50 or 60 minutes.
It's 60 with the questions.
Okay, then I'll do 50. Okay. So I have an aside about the family of black holes, which I said I would ignore in this talk, but now, because I have time, we won't ignore, which was this family of black ring solutions. Okay. So this is a, let me recall, this was a explicit metric, stationary matrix of stationary asymptotically flat solutions, which are again biaxially symmetric in the sense that I explained before. But now they are completely independent from this other family of Myers-Berry solutions in the sense that now the event horizon has a different topology than the one of Myers-Berry black holes. And it has this ring type topology as 1 times S2 when you intersect the event horizon with the Cauchy hypersurface. Okay, now, as I emphasized before, these high-dimensional black holes can have sort of very different properties from the point of view of the geodesic flow. So in the case of these solutions, the surprising property is that some of these black rings, maybe this here, I mean some members of this black ring family, that meet stable trapping for null geodesics now. Okay. And this is something I've actually observed already in my PhD thesis. So some interesting question. One interesting question that maybe one could think about is the effect of this null stable trapping in the case of the massless now Vlasov equation on fixed black ring backgrounds, and then maybe more ambitiously trying to maybe understand what could be the dynamics of these solutions as solutions to the Einstein massless Vlasov equations. Okay. You have a question? No, no question. Okay. Another question has to do with the behavior of general solutions to the wave equation on these black rings admitting stable trapping of null geodesics. So there is work of mine where I prove that solutions to the wave equation, they exhibit this following property. So either uniform boundedness fails, or if it holds, that will only decay logarithmic in time. Okay, so if uniform boundedness holds, then by some general, it's actually a general result by Yorgos Moskidis, that we know that if uniform boundedness holds, then you will at least decay logarithmic in time. And what I've shown in this work is that actually this logarithmic decay, in the case of these black rings, is sharp. So you can really only decay logarithmic in time. So what remains open is this dichotomy that doesn't clarify if uniform boundedness really holds or not. Okay, and this is sort of interesting and maybe a future question that would be nice to understand. And this is a related work by Yakov and Toneanu, which which in a way has to do with the strategy and the technique that you might want to use to approach this uniform boundedness problem in the case where you do not expect to be able to prove an integrated decay estimate. Okay, proving uniform boundedness in the case of Kerr, you typically prove first integrated decay and then establish uniform boundedness. Whereas in this case, because you know that if uniform boundedness holds, you only decay logarithmically, you won't be able in the first place to prove integrated decay. If that makes sense for you. Okay, perfect. And also, so the questions have to do with the nonlinear effect of this slow linear decay. I have some numerical work with Cardenas, Avendano, Pretorius, and Sullivan, where we look at some model spacetimes where stable trapping for null geodesics is present, and we study the dynamics of nonlinear waves on this fixed background. And there's also an analogy and works in the case of asymptotic ADS black holes, where the stable trapping of null geodesics is also present because it's low decay of the linear wave equation on these spacetimes. And then it is there also open and interesting to understand what the effect of this low decay will be for the nonlinear dynamics already at the scalar level, where there is recent work by Kere and Moskilis on nonlinear waves on fixed structural ADS backgrounds with reflective boundary condition and some numerical simulations by Pau and Rossi. I think I'll stop here. Thank you very much.
Thanks.